introducing infinite series and finite series, also the partial sum. So let me introduce a summation symbol. So this is a summation symbol. How do you read this? This is called the summation of ai, where I goes from 1 to infinity. I is the index. And then this is the summation symbol. Summation symbol means sum. Sum means you are adding up numbers or variable. And then 1, I equals to 1. 1 is the lower limit, and then infinity on top is the upper limit. So this is the sum of ai, where I goes from 1 to infinity. Is pretty easy to interpret. So when I is equals to 1, you have a1, I equals to 2, I equals to 3, 4, 5, 6 to n, and then keep on going all the way to infinity. And then I, so I equals to 1, this is the lower limit, and then the upper limit is a subscript infinity. So this is called an infinite series because this is the sum of infinitely many terms. So what is the difference between series and sequence? Sequence is a list of number. Once again, sequence is a list of numbers. Series is the sum of this list. So sequence, let's say you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is a sequence. It's a list of numbers separated by commas. And then series is the sum of the entire sequence. So when you write a series, you should write 1 plus 2 plus 3 plus 4 plus 5 all the way to plus 10. That is called a series. What is the difference between infinite and finite? Infinite is you are adding up infinitely many terms. Finite is there is an end. There is a stopping point from I equals to 1 to n of ai. This is a1 plus a2 plus a3 plus a4 plus a5 plus an. So there are n terms. N is countable, right? So let's say n is equals to 100. I know that I am adding up 100 terms. When n is equals to 58, I know that I am adding up 58 terms. So 58 terms, 58 is a countable value, so we call this finite series. And then this has another name. This is called n partial sum of the sequence. And then for the summation, for the series, there are some properties. The first one is summation. I goes from 1 to n. This one doesn't have a subscript. This is not an ai. This is just a constant. So what is the sum equals to? So let's say this c is equals to 10. You are finding the sum of 10 where I goes from 1 to n. So what is that means? That means you are adding up a bunch of 10s. How many copies of 10? If you go from 1 to n, then there are if you are going from 1 to 100, then there are 100 copies of 10 adding together. As a result, the sum is equals to 10 times 100. Let's say n is equals to 50. I goes from 1 to 50. Then there are 50 copies of 10 adding up together. So 10 plus 10 plus 10 plus itself 50 times is equivalent to 10 times 50. So that is what the first property means. And then the second property, finally, you have an ai. So I goes from 1 to n. You are doing c times a1 plus c times a2 plus c times a3. So every time you write a new term, there is a c, a constant in front of that. Another way to write that is you factor out the c. So let's say 5 times 2 plus 5 times 3. Do we agree that we can just factor out the 5? We can write this as 5 times parenthesis 2 plus 3. So same thing here. We factor out the c. Okay, and then c times the sum of ai. So for the summation of ai plus bi, this is adding up two different sums. For difference, you are subtracting two different sums. Sometimes when you move on to, or when you study more series, they will just use a symbol. So sometimes we already know that this is from I to n, so people just skip that, just write, hey, we are talking about the sum of ai plus bi. Since everybody knows that that is from I to n or I to infinity, we will just skip those. So we can just write this quick. All right, so now we just introduced infinite series and finite series. Let's do some basic exercise. The first example that I would like to do is I want to find the sum of 2i, where I goes from 1 to 4. So what happened when I is equals to 1? You have 2 times 1 I equals to 2, I equals to 3, and I equals to 4. You add that, so that is equals to 2 plus 4 plus 6 plus 8, then that is equals to 20. So this is the first sum. Yep, it's pretty easy. How about the next one? I goes from 0 to 3. So this is from 0 to 3. So I goes from 0 to 3. So this is a 0 plus 2. And then 1 plus 2. And then I equals to 2 plus 2. And then I equals to 3 plus 2. So this is I goes from 0 to 3. The reason I create this example is because I want to let you know that I doesn't have to start at 1. I can start at 0. I can start at 2. I can start at 3, depending on where you want to start. But usually, as an introductory level, we always let I start at 1. So what is this equals to? This is a 2 plus 3, 0, 1, 2, 3, right? Okay, so 4 terms. 0 plus 3 plus 4 plus 5. So this is 9 plus 5. 9 plus 5 is equals to 14. So the sum is equals to 14. Okay, did I make mistakes right here? Nope, because I wrote a mistake on my notes. It's okay, I didn't present the mistake in my video. Okay, the next problem is interesting. Look at this. Summation, I goes from 1 to infinity. 5 divided by 10i, and then I is the exponent. So without doing any math, you might be thinking, hey, look, this is an infinite series, right? That means you are adding up infinitely many terms. All right, so this triggers my number sense. You are adding up infinitely many numbers. Am I making sense right here? You are adding up infinitely many numbers. Each number has its own value, right? You are adding up infinitely many of them. So let's say you have a dollar. You are adding up infinitely many of $1, so you are going to get an infinity, right? Okay, so based on this concept, is this summation equals to, I should say, is this series, the sum equals to infinity? Let's find out. So this one, when I is equals to 1, what do we have? When I is equals to 1, we have 5 times 10 to the first, and then 5, did I say times? 5 divided by 10 to the second, 5 divided by 10 to the third. Okay, you know what? Let's make this look like a 2 and a 3. 2 and a 3, and then a 4, and then a 5. With a 4, 10 to the 5th. Okay, what is that equal to? This one we will have to use the decimal. 5 over 10 is a 1/2. 5 over 100, that is a 0.05. 5 divided by 1,000. And then 10,000. And then this one, if you catch the pattern, then that will be 4 zeros, right? And then a 5. So basically, if you keep on going, so eventually you are going to get 0.55555, right? A bunch of 5. 5 is repeating. Now, I know it looks like it is done, so this is a perfect example that explains when you are adding up infinitely many numbers, the sum is not necessarily infinity. You are adding up so many numbers, it looks like you are increasing the value indefinitely, right? But you have to know that it doesn't have to be infinity. Do you know why? Here is the reason. Let's look at the denominator. 10 to the third, 10 to the fourth, 10 to the fifth, 10 to the sixth, 10 to the 1,000. What happened? The denominator is getting so big, right? When you take a 5 divided by a huge denominator, what is going to happen? The quotient is nearly a 0. So as the ice becomes really, really big, you are just adding up a bunch of zeros. So therefore, the sum is really depends on the first few terms, because as you raise 10 to the 1,000 power, that is so huge. Take 5 divided by that is just a 0. Yes, you are adding up infinitely many numbers. But as I becomes really big, those numbers, those quotients are just a 0. So the sum really depends on the first couple numbers. Now, the second reason why I picked this problem is because, hey, how do you put this back to a fraction? In fraction, hey. How? So here is how. So first of all, this is a technique that you have to study. First of all, we let x equals to that, right? And then you have to write this. You have to put a decimal. You have to put a decimal where the number keeps repeating up after that. And then to get a 5 point something, do we agree that we have to multiply both sides by 10? Right? Right? So after the decimal, the numbers are repeating. I don't care what is in front of the decimal, but after the decimal, the numbers are repeating. Right? And then you subtract these two equations. 10 minus x is equals to 9x. This is equals to 5, right? And then what is x equals to? X is equals to 5 over 9. So as a result, this is equals to 5 over 9. That is the sum, not infinity. Interesting, right? Okay, I have another one for you here, the yellow one. 7 divided by 1 over 10 raised to the k. So this one, the way I do this is, I will just factor out the 7. I want to match the color. This is the color that I have to match. So this is equals to, from k equals to 1 to infinity, we have 7. And then 1 over 10 raised to the k. So that one is a 7. And then multiply when k is equals to 1. When k is equals to 2, when k is equals to 3, when k is equals to 4, and so on. Right? What is that in decimal? 7 times 0.1, 0.01, 0.001, and then 0.0001, and then keep on going. Right? So as the power becomes extremely large, do we agree that 110 raised to an extremely large power is nearly a 0? So therefore, the sum is not going to be infinity, because as I become so big, you are just adding up a bunch of zeros, right? So the sum really depends on the first couple numbers. And I want to know exactly what that equals to. So this one, let's don't talk about the 7. So this, we are going to get x equals to 0.11111, right? Many ones. I am going to multiply both sides by 10. So now, after this decimal, the numbers keep repeating. And then you subtract these two equations. You have 9x equals to 1. So therefore, x equals to 1 over 9. 1 over 9. Then as a result, this is 7 times 1 over 9. And then the sum is just equals to 7 over 9. And then this is the sum, not infinity. So that's why this problem is so interesting, and I have to discuss this problem in my video. Okay, 2 problems left. Let's do it. The next one is I equals to 1 to, from 1 to 4, I factorial divided by 2 to the I power. So this one, I equals to 1 factorial, 2 to the first, I equals to 2 factorial, 2 to the second, and then 3 factorial, 2 to the third, and then 4 factorial, 2 to the fourth. All right, so 1/2 plus 2 over 4 plus 6 over 8 plus 24 over 16. That one, common denominator, you work on that, 29 divided by 12. Okay, last one. The last one in blue. I am going to copy and paste this, so we don't need to scroll up and down, copy, and then let's paste that over here. All I need is the 6th and the 8th partial sum. Okay, 6th and the 8th partial sum. So that means I goes from 1 to 6, right? So I goes from 1 to 6. So we have 2 times 1/3 to the first, 2 times 1/3 to the second, and then 2 times 1/3 to the third, to the fourth, to the fifth, and then to the sixth. The sixth. So this one will be what? This one will be all you have to do is you just add them, right? So this is 2 over 3 plus 2 over 9 plus 2 over 27 and then plus 2 over 81 and then plus 2 over 3 to the third power is 243 and then plus 2 over 6 power is 729. I mean, did I say 2 to the third power? It's 3 to the third power. And then this one, when you add everything up, that is equals to 728 divided by 729. So that is the sixth partial sum. Partial sum. So what is partial sum? Partial sum means this is an infinite series, right? So I goes from 1 all the way to infinity. Partial sum is you have a long list, you have a long line. Partial sum is part of the line. So imagine that you are adding up infinite many numbers up. Eighth partial sum is I only need to add the 8 terms up. How about the eighth partial sum? The eighth partial sum will be 728 divided by 729 plus the 7th and the 8th. So 2 to the 1/3 to the 7th and then 2 to the 1/3 to the 8th. So whatever that equals to, that is the eighth partial sum. That doesn't sound like a partial sum. Okay, the common denominator, I leave that one for you. All right, so this is the end of the introduction to infinite and finite series. If you like the way I introduce this, give me a thumbs up. If this is what you want to watch, give a subscribe to my channel. Truly appreciate for your help and support. And as always, I will meet you all in the next videos. Signing out.